Hi, I'm Bolan Li. Welcome to my CGO paper presentation. The topic of the paper is DJXPerf, identifying memory inefficiencies via object-centric profiling for Java. Now, the Java programming languages has been around for more than 25 years, still is regularly among the top two programming languages used in the world. Java can be used to build applications for a wide range of platforms like desktops, servers, mobile phones, tablets, televisions, and web browsers all use Java. And Java developers want their Java-based applications to run faster and consume less energy. So Java performance concerns are everywhere. After we know the profiling workflows, next let me introduce some classical profiling techniques. Classical profiling techniques usually target hotspot, that is high resource utilization, such as high CPU usage, cache misses, access latency, memory allocations, and some other hotspot metrics. Hotspot analysis is indispensable, but it cannot tell whether the resources are well spent. For example, the computation in a hotspot can be completely useless. A heavy burden is on the user to make a judgment call on whether there is a scope to optimize a hotspot. Also, hotspot analysis cannot detect the data locality issues, which is the main focus of this paper. So what's the inefficiencies that DJXPerf can find? First of all, DJXPerf can detect traditional locality issues that happens in Java program. There are two traditional data locality issues, temporal and spatial. Let's look at this example. Here at line 3, variable sum is being used again and again, which shows the temporal locality. The value of array is being accessed in order. For example, array 0, array 1, array 2, and so on. This shows spatial locality because arrays are adjacent memory blocks, so data near to current memory location is being fetched. Besides the traditional locality problem, garbage collected languages such as Java have another unique locality issue, the memory bloat. Memory bloat occurs by allocating and initializing many objects whose lifetime do not overlap. For example, allocating objects in a loop where the object's lifetime is only the scope of the loop body. Since garbage collection happens sometimes later in the future, memory consumption increases. Memory bloat can be seen as a case of like both spatial and temporal locality because accessing a large number of independent objects results in accessing different cache lines, which means there's little or no reusing of a previously accessed cache line. In addition to traditional locality issues and memory bloat, DJXPerf also can be used to detect the NUMA inefficiencies. NUMA is the short name for non-uniform memory access, and it is a computer memory design used in multiprocessing. In NUMA, processors in the same physical location are grouped in a node with its local node memory. In NUMA system, there will be more than one such node, and these nodes will use a shared interconnected mechanism to transfer data between them. In such a case, a processor accessing its local node memory will be much faster than the same processor accessing memory from remote node memory. So minimizing the node of remote accesses is essential for high performance computing. Okay, so far we know the three different types of inefficiencies that the DJXPerf focuses on. To detect these inefficiency issues, we propose the object-centric analysis in the DJXPerf. So what's the object-centric? To better explain the idea of object-centric, here I have a comparison between code-centric, and object-centric. In the top half of this code, it allocates three objects here, IDX, temp, and the pH from line 2 to line 4 for computation. Then the program accesses the allocated objects from line 8 to 11. In the left bottom of this picture, the code-centric profiling pinpoints that line 9 and 11 account for all of the L1 cache misses. So line 9 has 70% of L1 cache misses, and line 11 has the rest of 30%. This is the only thing the code-centric can tell. However, in the red bottom, the object-centric profiling can further associate metrics with individual objects, indicating that the objects IDX and temp account for the most cache misses. So the object-centric analysis not only can pinpoint code locations, but also it can identify which objects suffer from higher L1 cache misses. So we would say that object-centric analysis can provide more profiling information than the code-centric analysis. Here is about the motivation of combining object-level information and other metrics for locality optimization. I'm going to show two problematic code snippets suffering from memory bloat. Here in the first code snippet, the object allocation set at line 5 creates a float array of values in the method makeRoom. Since the method makeRoom is called inside a loop, so this allocation set is repeatedly invoked about 2,400 times, resulting in memory bloat. From the optimization, we move this array allocation outside this loop that encloses the method makeRoom and replace it with a static object array. So this optimization addresses the memory bloat and has a 1.15 times speed up. In the second code snippet, the memory bloat occurs at line 3, which repeatedly allocated the object collector around 15,000 times because the search method is iteratively invoked in a loop. We can also move the allocation set outside the loop, enclosing the method search. While this optimization addresses the memory bloat, it does not bring any noticeable speed up. So this is two examples reveal that basing the optimization only on allocation frequency does not necessarily have performance benefits. This motivates the need for the additional locality metrics. In fact, DJXPerf measures L1 cache misses on memory access of objects allocation set. For example, DJXPerf reports that accessing the n-values array has 21% of total L1 cache misses, while accessing the collector objects has less than 1% of the total L1 cache misses only, which explains the different speedups obtained from the optimization. So object-centric analysis with the L1 cache miss metric is desired to determine whether locality optimization can have significant speedups or not. Next, I'm gonna give the overview of DJXPerf's object-centric analysis. So DJXPerf includes two agents, a Java agent and a JVMTI agent. The Java agent adds lightweight bytecode instrumentation to capture object allocation information during execution, such as allocation context and the address range of objects shown in this figure. The JVMTI agent subscribes to Java's thread creation callbacks to enable PMU to simple memory accesses. When PMU interrupts a thread with a sampled address, DJXPerf associates the address seen in the sample with the Java objects enclosing that address. So this process is called object attribution. Next, I'm going to elaborate on each agent and discuss their interactions for the object-centric analysis. So DJXPerf leverages a Java agent to capture object allocation. So the Java agent is based on the ASM framework. The Java agent scans Java bytecode and instruments four object allocation routines: new array, a new array, and a multi-new array. The Java agent inserts pre and post allocation hooks to intercept each object allocation and returns the object information, for example, the object pointer, tab, and size, via the user-defined callbacks. DJXPerf leverages a GMTI agent to sample and collect memory accesses. With the help of GMTI, DJXPerf can intercept the Java thread start, while DJXPerf configures PMUs to sample precise events. For example, to sample the cache misses, we can use the L1 miss event. To sample the TLB miss, we can use the DTLB load misses event. And to sample the memory access latency, we can use the load latency event. Still, we can use many other precise events. And DJXPerf also installs a signal handler to precise PMU samples. On thread termination, DJXPerf stops PMU and produces a profile for each thread. So besides controlling PMUs, DJXPerf also utilizes the GMTI agent to capture the calling context for both PMU samples and the object allocations. So here's about identifying objects in DJXPerf. So how to represent an object to a developer is a challenging question. We use the allocation call paths to identify different objects. An application can create multiple objects via a single allocation site, for example, in a loop. In our approach, all such objects will be represented by a single call path, because different objects allocated at the same call path are likely to have similar behavior. For how to attribute PMU samples to objects, DJXPerf utilizes an interval split tree to maintain the memory ranges allocated for all the monitored objects. So this figure shows an example of an interval split tree. So in this tree, each node has its own interval, and here we use its left bound as the key to sorting this tree, and the value in each node represents the maximum memory scope contained in a subtree. On each PMU symbol, DJXPerf uses the effective address presented by the PMU to look up into the split tree. The lookup operation returns the objects whose memory range encloses the sampled address. So DJXPerf then attributes this PMU matrix to the object's allocation call path. Also, as I showed before, DJXPerf can be used to detect the NUMA remote access. Here are the basic ideas. On the PMU symbol, DJXPerf uses the effective address to identify a memory page in libNUMA library function, NUMA move pages. The NUMA move pages not only can move a specified page to a NUMA node, but also it can return the NUMA node where the page is currently residing. So in this way, DJXPerf can identify in which NUMA node the current object is allocated. Here we denote this NUMA node as node 0. To identify the access node on each PMU symbol, DJXPerf uses the perf sample CPU identifier, which contains the CPU number. to show which NUMA node the current object is accessing. Here we denote this access node as node 1. If node 0 and node 1 are distinct nodes, as shown in this figure, then DJXPerf reports a remote memory access for this object. So this figure shows two NUMA nodes, and we can see that there is an inter-socket connection between them for this remote access. Here is a whole workflow of DJXPerf, which consists of an online data collector and an offline data analyzer. From this figure, we can see that there are two ways to enable the online data collector. First, if we need to profile Java source code as soon as the JVM starts up, we can launch DJXPerf as an agent by passing JVM options. If the JVM is already started, we can launch DJXPerf to this running JVM. This is particularly useful for monitoring long-running programs such as web servers or microservices. The collector starts the measurements and generates a profile file per thread. The analyzer then aggregates all of the profile files from different threads, sorts the metrics, and generates one final overall profile file, which shows the problematic objects to the developers. So by now I have introduced how DJXPerf overcomes some JVM challenges, and I just want to mention a main challenge here is the garbage collection. Here I'm going to talk about the implementation details that enable DJXPerf to handle GC inside JVM. So the garbage collector complicates the object-centric attribution because GC reclaims the memory of unused objects and moves objects for more compact memory layouts. So the trigger of the GC thread is determined by JVM, which is transparent to Java applications. So ignoring GC, DJXPerf may have incorrect object attribution. So here is an example of an incorrect object attribution with GC interference. So here we assume GC reclaims or moves an object O1, which memory can be reused by other allocations, say object O2. So in this case, O2 may incorrectly attribute PMU samples that touch O2 to O1. So this is an incorrect object attribution, and handling GC is necessary in DJXPerf. Unfortunately, JVM exposes limited information about GC via JVM-TI, because JVM-TI only provides hooks to register callbacks on GC start and end, with no insight about the individual object behavior. For example, JVM-TI cannot tell whether which object has been moved or reclaimed. So in our paper, we offer solutions to handle the GC interference in the JVM. First, the solution for the object movement by GC. Our solution is based on an important observation from the source code of OpenJDK. So GC moves objects using the memory move function. So we overload memory move to obtain the source and the destination of every moved object and update the memory ranges associated with this object in the split tree. However, updating the split tree upon each memory move invocation is costly. So instead, the DJXPerf creates a relocation map for each thread to record the moved objects. For example, in the relocation map, the key of the map is the object source address. The value are the destination addresses and the object set. So I want to update the objects in the relocation map in a batch at the end of each GC invocation. Next, the scenario of GC reclamation is simple. So whenever a memory interval is allocated for a new object and that memory interval overlaps with any existing memory intervals in the split tree, at this time, the DJXPerf can just remove the overlapped memory intervals from the split tree and add the newly allocated objects to the split tree. And the following several slides, I'm gonna show the evaluation results of DJXPerf. So the first is the overhead analysis. Here the top figure shows the runtime overhead, which is the ratio of the runtime under monitoring with DJXPerf to the runtime of the corresponding native execution, and same for the bottom memory overhead. To quantify the overhead of DJXPerf in both runtime and memory, we applied DJXPerf to a number of well-known Java benchmark suites, such as the most recent JVM parallel benchmark suite, Renaissance, and we also test the DJXPerf on two traditional Java benchmarks, DACouple and Spec JVM. During the experiment, we run every benchmark 30 times and compute the average and error bar. From the last column of these two figures, we can see that DJXPerf typically incurs 8% runtime and 5% memory overhead. Here is a Java application named Object Layout. So I'm gonna use this application to show how to use DJXPerf to detect memory bloat issues and optimize them. So this figure shows the snapshot of DJXPerf's GUI for intuitive analysis. So top pane of the GUI shows the Java source code. The bottom left pane shows the object allocation in red and the access in blue in their full call path. And the bottom right pane shows two metrics, L1 cache misses and object allocation times. So the GUI in this figure shows one problematic object at line 292, which is highlighted with the yellow line in the source code. The GUI shows that this object is allocated for 217 times. There are multiple simple access associated with this allocation set, and they count for 30.4% of L1 cache misses of the entire program. So to save the space, I only show one access that accounts for most of cache miss. So the right frame at the bottom shows another 6 access locations associated with this same allocation site. With further investigation of the source code, we found that the problematic object is an array named int addressable element. So since the life cycles of different instances do not overlap, we can allocate a single object instance and reuse it without creating more instances. To avoid memory bloat, we move the allocation set out of the method because this method is invoked repeatedly. We optimize 3 other problematic objects with similar methods, and our optimization reduces total cache miss by 76% and has a 1.45 times increase in throughput. Here I give a table that overviews the performance improvements on real-world Java applications guided by DJXPerf. For each Java application, we pinpoint the problematic code location and what the inefficiency type is. From this table, we can see DJXPerf detects three different types of issues. The first one is excessive memory usage in nested loops. The second one is problematic data with high L1 cache misses. So this category is related to the traditional locality issues such as temporal and spatial locality. And the last one is the Newman remote access, which is pretty useful in the current multiprocessing architecture. And for the optimization in this table, we show how we fix these inefficient issues. For example, moving the allocation side out of the loop, or using some traditional techniques like loop interchange or loop tiling. For Newman remote access issues, we allocate problematic object size interleaved on all Newman nodes. And we use four metrics to measure the performance benefits. They are optimization speed up, L1 cache hit increase, L1 cache miss per kilo instruction reduction, and the number of GC reduction. Besides this performance gains from the different metrics, we also have submitted our optimization patches, and some of them got upstreamed in real-world applications, such as the object layout and fun bugs. And finally, this is the conclusion part. So this work, categorized the varieties of data locality inefficiencies manifest as wasteful object allocation and memory operations. This work developed DJXPerf to pinpoint data locality inefficiencies in Java programs. And DJXPerf takes advantage of lightweight, novel object-centric profiling techniques and can be applied to unmodified Java application, virtual machine, and OS. Guided by DJXPerf, some Java applications obtains non-trivial performance gains. Also, this work has contributed to the community since some optimization patches are upstreamed to the real-world Java applications. All right, that's all of my presentation. Thank you.